Hi, my name is Mohammed Faris. I'm here to present our co-analysis of Fourier series. This project to study the signal behavior in both the time and frequency domain for different harmonic. Firstly, we need to determine the parameter. The first part of our MATLAB code calculate the Fourier coefficient using the sine C function and reconstructs the time domain signal for different harmonic level. The second part of our code calculate and plot the Fourier coefficient in the frequency domain for 5, 10, and 20 harmonics. So in the figure 1, the top plot show the signal reconstruct with 5 harmonies. The approximation is rough with noticeable ripples due to Gibbs phenomenon. The second plot with 10 harmonics show an improved reconstruction. The edge of the square wave are sharper and the ripple are less pronounced. The third plot with 20 harmonics closely resemble a square wave. The ripple are minimal, but they still appear near the edge. This demonstrates that increasing the number of harmonies improves the reconstruction accuracy. In figure 2, the first plot for 5 harmonics show the Fourier coefficient with decreasing amplitude as harmonic order increases. The second plot for 10 harmonics extend the frequency spectrum, showing additional components. In the third plot for 20 harmonics, the spectrum becomes richer, capturing more high frequency component. The sine C function governs the amplitude, which decreases as frequency increases. From the result, we observe time domain. Increasing harmonic improves square wave reconstruction, but ripples persist near sharp transition. Frequency domain. Fourier coefficient decrease with harmonic order due to the sine C function. Higher harmonics contribute less but are crucial for capturing sharp edge.
Hi everyone, my name is Muhammad Anik Wazir bin Danilo and my matrix number is DE23003 So if you look at my screen, this is my MATLAB code and the code will come out with this result. So I am focusing on the design and analyze of a low pass RC filter with cut-off frequency of 870 kHz. So the first part of the code is to calculate the frequency response of the filter, which is using the formula 1 over square root 1 plus f over fc squared. So the continuous frequency response is plotted on both linear and visible scale, highlight how the filter attenuated frequency beyond the cutoff. The red dashed line mark the cutoff frequency at negative 3 dB, which is where the signal power dropped to half. Next, I have evaluated HF at the discrete harmonic frequency corresponding to the Fourier coefficient of the input signal in the code MATLAB. So this is shown in the third subplot where the filter attenuation of coefficient higher harmonic is clearly visible. The closer the harmonic is to the cutoff frequency, the more it is attenuated, which smooth the signal in the time domain. Overall, this effectively demonstrates the theoretical behavior of RC filter in both the continuous and discrete frequency domain. With clear visualization of the filtering process, this result will later be used to reconstruct and analyze the filtered signal in the time domain. That's all for me. Thank you.
Hello everyone, my name is Kim Yao and I'm going to present about the part B, which is the filter signal analysis. First, we create a new figure window for the time domain reconstruction of filtered signal for 5, 10, and 20 harmonics. Next, we create a subplot, which is one of 3 rows in a single figure for the current harmonic count. And then we plot the real part of the reconstructed filter signal against the time. Lastly, we label the x-axis as time in seconds and the y-axis as amplitude. Next, after we run the coding, we will get this filter signal in time domain with 5 harmonic, 10 harmonic, and 20 harmonics. From the waveform, we can observe that the period t is increases when the harmonic value increase after the signal is filtered. So that for the frequency domain plot for filtered Fourier coefficients for 5, 10, and 20 harmonics, we opens a new figure window for plotting the frequency domain coefficient. Next, we create a stem plot of the filtered Fourier coefficients. Finally, we label the x-axis as harmonic index and the y-axis as the magnitude of the filtered coefficient and enable the grid lines. So this is the graph after we run the second part of the coding, we will get the frequency domain of filter signal with 5 harmonics, 10 harmonics, and 20 harmonics. The graph is different from the magnitude of the filter coefficient was decreased after the signal is filtered.
Hello everyone, my name is Kai. Now I will present about the circuit of this project. This circuit is show the low pass filter, and in this circuit, to get this capacitor, we need to use the formula. The formula is this. The FC given is 870 kilohertz, and the FC formula is equals to the 1/2 pi RC. If R if let the R equal to 10 kilo ohms, we will get the capacitor is 18.29 picofarad. Now therefore we will get this circuit and when we run this circuit, we will show the graph like this. Therefore, in this circuit, it will show the graph, the curve graph, which similar with the MATLAB. Therefore, this circuit is verified by the MATLAB because the graph is similar with the MATLAB.
My name is Niwan J. Today I will going to present about the part 4 to study about the duty cycle effect with different harmonic using MATLABs. These are the code we will use for study the duty effect with different harmonies. From this code is used for define the cycles to analyze as a percentage of the signal periods from 10%, 20%, 30%, 70%, and 80%. And this is the look through different number of harmony from the n harmonic arrays. And this is a code for the look through each duty cycle in the duty cycle arrays. And this is the formula we use for calculate the pulse rates. And this is the formula we use for calculate the Fourier coefficients for new duty cycles. And this code used for calculate the time domain reconstructions. And these two codes used for plotting the time domain signal graph and frequency domain reconstruction graph. After we run, we will get these three results. This is the 5 harmonic graph. This is a 10 harmonic graph. This is 20 harmonic graph. As you can see from the time domain signal graph, as we increase the harmonics, the edge of the pulse will become sharper. You can see the difference. The edge of the pulse will become sharp and better, resembling the ideas of rectangular shapes. From the frequency domains, it is easy to help us to analyze better understand the signal energy distributed across the different frequencies. As we use a low duty cycle, the energy distribute across a wide range of harmony. As we increase the duty cycle, the distribution becomes smaller and smaller. And with different harmonic, the distribution range will become smaller and smaller. The narrowest pulse means low duty cycles, as a broad frequencies contains means they need more harmonics for accurate reconstructions. For the wide pulse high duty cycles, concentrate energy in few harmony, making the signal easy to reconstruct. That's all from me. Thank you.